Sorry, I'm not very, as I said, I'm not very familiar with these online tools. I'm starting to have my online teaching this semester, and I'm not expert, as you can see, with Teams especially. So anyway, good afternoon, everyone in the end, and thank you for being here for this last lecture of the second day of the SmartThings Training School. It's a real pleasure for me, despite all this inconvenience, to finally get to meet you, and even if not in person, of course, but only in remote mode. And I really hope that we are going to have new opportunities to meet each other in person, maybe also to collaborate directly. But for now, we are just stuck on our sides of the screen, and we just have to spend 1 hour together online. So the title of my presentation, if you confirm that you can see it, is Non-Destructive Testing for
Yes, everything is working perfectly, so.
Very good. Okay, so here you can see the outline of my presentation. So first I'm going to make a short introduction just to introduce myself and explain the reasons and the structure of my lecture. And then I will focus on some of the non-destructive testing methods that are mostly used for the characterization of structural materials and structural components. So nothing really advanced, just some simple key concepts and examples related to ultrasonic methods and durability tests. For both these classes of non-destructive testing methods, I will also provide some operational notes to bring your attention on influencing factors that you need to take into account when you have to implement some of these testing methods for practical applications, but also for research application. And finally, some conclusive remarks regarding the project that you're working on for this training school. But first, let me tell you something about myself and my research group. I am an assistant professor at the Department of Structural, Geotechnical and Building Engineering of Politecnico di Torino in Italy. I have a background in civil engineering and structural mechanics, and I work on the development of advanced material for the construction sector, mostly self-healing and alkali activated materials. And I also work on mechanical characterization of materials and structures and on structure testing. Most of my research in collaboration with some colleagues and friends from my institutions, and among them there is Professor Jean-Marc Tuliani, who is an associate professor of material science and technology and is also a member of the supervisory board of SmartThings. Then Giovanni Anglani, who has just discussed his PhD under my supervision, when he focused his dissertation on self-healing via cementitious macrocapsules. And I guess he should be attending this training school too. And finally, Professors Marcos Calerandi and Antonio Liozzi, who are physicists and have been collaborating with me for a long time in the field of non-destructive testing via ultrasonic techniques. So based on this research background and collaboration network, I've been asked to give a lecture in the frame of this training school. And of course, I feel honored and I thank the organizers for this opportunity. So in my intention, the main goal of this training lecture is essentially to stimulate the intellectual curiosity towards non-destructive testing methods and to promote their use for the characterization of self-healing systems. Therefore, I will not be presenting an extensive review on the matter, for which there won't be enough time and I won't be sufficiently qualified to. Instead, I will simply present the basis of some most widely used non-destructive techniques, along with a few examples taken from the scientific literature relating to their application in self-healing, and also references for further reading and learning insights. So as I said, also some operational notes. They will be presented to highlight the main influence factors that may affect the test outcomes and provide inputs for practical application. So if I succeed in my goal to stimulate your curiosity, then you will probably come up with some new personal ideas for the implementation of a non-destructive testing plan related to the project that you're working on for this training school. And such a testing plan should contribute to evaluate the feasibility and effectiveness of the self-healing solutions that you're going to propose at the laboratory development stage, and then to monitor their performance on the field. You don't really need to possess any high-level prerequisite to follow this lesson, just some basic knowledge of physics and mechanics, on the damage phenomena in concrete structures, and of course in self-healing mechanisms. As for the reading material, I am reporting here only 3 nice review papers. The first one is a state-of-the-art report on the experimental characterization methods for self-healing cementitious materials. It has been produced in the frame of the cost action circles, and it's not entirely focused on non-destructive testing, but it covers this topic along with others. A more specific review on non-destructive testing for self-healing is given in the second paper, which is authored by Professor Didier Snurk and co-workers. And finally, the third paper addresses even more specifically the topic of non-destructive testing for self-healing via ultrasonic methods. And if you're interested in further reading, to go more into details, you can refer to the studies overviewed in these papers, plus some other ones that I will mention during this lecture when I will present some examples. Why is it important to deal with non-destructive testing? Well, by definition, non-destructive testing does not produce any damage to the structure or the element being investigated, and this non-destructive character contributes to widen the field of application of these techniques. So they can be applied on site to monitor the behavior of full-scale structures or their components, and this makes them suitable to assess self-healing in real operating conditions, once that some self-healing solution has been activated. Otherwise, they can be applied to monitor the behavior of specimens or prototypes in the laboratory. And since the specimen is not damaged during the inspection, it means that it remains available for further testing, which is obviously not the case with destructive testing. So NDT in the end is the only possible way to investigate the time evolution of a certain phenomenon without changing the reference, the observation object, that is the specimen or prototype under investigation. And therefore NDT is also very helpful for the purposes of developing new self-healing solution or optimizing the existing one. So this is a possible way to classify non-destructive testing based on the possible operating condition in the lab or on the field. But in the second review paper that I mentioned before, the authors propose another possible way to characterize non-destructive testing, other than based on their operational condition. They distinguish non-destructive testing techniques based on their application. So they identify methods that can be used, for example, to quantify the crack closure, to characterize the encapsulation or the protection mechanism of the healing agent, to characterize the healing agent itself, or to analyze its distribution within the volume of the element tested. And these techniques can also be used to study the trigger mechanism for self-healing, or to characterize the healing efficiency and healing performance over time, which is the scope of this lecture. So therefore, among all the numerous and diversified possible NDT methods as reported in the review paper, we will examine only those based on ultrasonic and surface transmission methods and on durability tests such as water permeability and water absorption, because, as I said, they can contribute to the characterization of the self-healing efficiency and healing performance in time. And they can do it both on site and in the lab, as far as ultrasonic methods are concerned, or prevalently in the lab for research and development purposes when considering durability tests. Let's begin with ultrasonic methods. You certainly know that ultrasound is a vibration that propagates through a transmission medium that can be a gas, a liquid, or a solid, as a wave of pressure. that is beyond the human audible range, that is to say, beyond 20 kHz on average, up to some hundreds of megahertz, depending on the application. And such a perturbation of the medium can propagate in the body by means of longitudinal waves, also called P waves or primary waves, in which the oscillation of material particles occur in the same direction as the propagating wave. Or the perturbation can propagate in the body by means of transverse waves, which are called also shear waves, S waves, or secondary waves because their velocity is lower than in primary waves. Or the perturbation can propagate along the surface of the medium with a rather complex particle movement that involves both longitudinal and transverse oscillation. There exist two types of surface waves: Rayleigh waves, which are produced by the interference of longitudinal and transversal waves with the boundaries and are characterized by an elliptic retrograde motion, and Love waves, which are horizontally polarized surface waves resulting from the interference of many shear waves and can occur only in layered media. And there are also other types of elastic wave, for example, in solids with dimensions smaller than the wavelength, or with interfaces in the wave direction, Lamb waves and torsional waves can be generated. And finally, there are Coda waves, which are generated in finite media and in particular in finite heterogeneous media, and they result from multiple reflections of the direct body and surface waves, plus multiple scattering, fusion, and other effects. And they are the last to be detected because they travel for longer paths in the medium before reaching the detector and contain more or less a diffused wave field. But however their origin, there are two ways to describe an elastic wave, either as a disturbance in all of space at a single instant in time, or as a disturbance as a function of time at a single point in space. So in the first view, we need to plot the magnitude of the wave disturbance at the given instant of time as a function of a distance coordinate. And in the second view, we will plot the magnitude of the wave disturbance at a given point in space as a function of time. So both these plots describing the wave look the same, just like the third figure that you see from top, except for levels and units on the x-axis. And the wave amplitude is the maximum displacement of the representative wave quantity with respect to the undisturbed equilibrium position. The frequency is the number of cycles per second of the wave quantity measured in hertz, and the wavelength is the distance between corresponding points on successive cycles, for example, between wave crests, and is measured in units of length. The polarization that needs to be specified for transverse waves only identifies the direction of particle oscillation in space. And the propagation velocity is the wave speed in space, and is a characteristic of the medium and of the type of wave, so it doesn't depend on the parameters of the source or the detector. There is a complex physical interaction between the elastic wave and the transmission medium. For example, the wave speed depends on the material density and the elastic characteristic. The wave amplitude depends on the material viscous characteristics, and there can be attenuation, reflection, diffraction, interference phenomena, etc. So this complex interaction with the transmission medium is exactly the reason why investigative ultrasonic wave propagation can provide information for material characterization. And therefore we need to generate, propagate, and detect some ultrasonic waves to explore the medium. And how can we do it? What we need is an ultrasonic transducer that is a small portable device, essentially composed of an external case in contact with the medium to be explored through the wear plate, that is usually a plastic membrane, electrical leads connected to a function generator on one side and to the electrodes of the active element on the other side. And the active element is a piezoelectric crystal that is a natural or artificial material characterized by the capability to generate an electric charge in response to an applied mechanical stress, and vice versa. So to undergo a mechanical stress when subjected to an electric field. So when excited with an electrical pulse or forced to vibrate according to prescribed laws, these crystals transfer their vibration to the medium they're in contact with in the form of an ultrasonic wave. And in this case, the ultrasonic transducer works as an emitting source. On the contrary, when the ultrasonic wave reaches the piezoelectric crystal, then such a vibration is converted into an electric signal that can be collected and transferred to an analog digital converter and then to a data acquisition unit. And in this case, the transducer works as a receiver. And since there is always a gap between the surface of the medium and the surface of the transducer, major reflection phenomena can occur at the interface. And for this reason, it's important to use a proper coupling agent that adjusts the acoustic impedance of the two and allows for wave transmission instead of reflection. And ecographic gels and oils are not very recommendable in cementitious materials since they tend to be absorbed through the pore of the material in a short time. So thicker couplings are more suitable, such as grease or wax or plasticine. Another important parameter is the range of working frequencies of the transducer that depends on the size and of the geometry of the crystals and have to be selected depending on the application. High-frequency transducers working in the range of megahertz are not suitable for cementitious materials because high-frequency waves tend to be attenuated very fast in these materials. 20 to 150 kHz is generally a good option, but we will go back to this point later. So this type of transducers allow for a variety of ultrasonic inspection techniques, and among them, those using ultrasound pulse velocity are some of the most widely used. Indeed, they are fast, easy to implement, they require a relatively low-cost equipment, they are suitable for on-site testing, and they have been used for damage assessment for decades, so there's a wide literature on this subject. And there are also some reference standards, such as the European Standard 12504, Part 4, or the ASTM Standard C597. Here you can see a scheme of how the test is performed. So when a synchronization system triggers a test, a timing circuit starts measuring the time, while a function generator transmits a pulse signal to the emitting transducer. Then the ultrasonic wave generated by the emitting source travels through the medium and eventually reaches the receiving transducer that collects it in the form of an electric signal. And this signal can be amplified and filtered and eventually provides a feedback signal to the timing circuit that gives a visual indication of the time of flight as soon as the wave gets to the receiver. And once the time of flight is known, the average ultrasonic pulse velocity can be calculated very easily based on the distance between the transducers, that is the shortest travel path. And in this way, the test can be conducted with direct transmission mode when the transducers are placed on opposite sides, on opposite faces, semi-direct transmission mode when they are placed on adjacent faces, or indirect transmission mode when they are placed on the same face. These transmission modes are listed according to their sensitivity in terms of velocity measurements, so whenever possible, direct transmission should be preferable. It's easy to understand that the pulse velocity decreases in the presence of damage with respect to sound material because the elastic waves travel faster in compact and dense media, and the presence of cracks alters these features, but also because the presence of cracks, especially large open cracks, does not allow transmission along the principal path, so the effective travel path increases and the apparent velocity measured diminishes accordingly. Vice versa, the velocity increases if the cracked medium is interested by a healing phenomenon. So if the crack density or the crack size and extent are diminishing, and therefore it's possible to define some damage or healing indicators as the ultrasonic pulse velocity ratio relative to a reference state, or simply the variation in time of flight for unvaried position of the transducer. Ideally, it's also possible to estimate the crack depth. This can be done by measuring the wave velocity in the sound material first, and then calculating the effective travel path based on the time of flight measurement provided by surface transducer placed aside of the crack. The assumption is that the effective crack path is the one that connects the transducers to the crack tip, or in other terms, the assumption is that no transmission can occur through the crack. And this is not always true, and also difficult to assess in real structures because of the irregular geometry of the cracks, with possible contact points or closed portions that would actually allow transmission, thus causing an underestimation of the crack depth. But anyway, this crack estimation method works quite fine in controlled laboratory conditions, so it can actually be used to evaluate the effectiveness of novel self-healing techniques in the lab, and possibly in association with other characterization methods. Let's see some results from the literature regarding the application of ultrasonic pulse velocity measurements for the characterization of self-healing. This picture is taken from a work by Professor Valtitterboom and her research group that dealt with the use of bacteria to repair cracks. It reports the absolute change in the time of flight with respect to the undamaged state as a function of different treatments adopted to repair concrete samples. In these concrete samples, cracks were introduced in a standardized way by inserting a copper plate in the molds, and when removed, the copper plate left a residual crack with a nominal width of 300 microns and a depth of 10 or 20 millimeters. And the samples were repaired with traditional external repair technique using epoxy and cement grout, or with bacteria-based strategies. And the results that you can see show a very good performance of the bacteria-based techniques that turned out to be practically as effective as the external repair techniques, with the additional advantages of being autonomous and less impacting than the environment, than the other one from the environmental point of view. Of course, these results are also clearly distinguishable from those obtained in the damaged state. Here's another work by Professor Ferrara and co-workers that presents the results in terms of pulse velocity ratio with respect to the undamaged state of concrete elements with or without crystalline admixtures subjected to cracking by three-point bending. So here the self-healing mechanism changes with respect to the previous study and relies on the stimulated autogenous healing promoted by crystalline admixture, but the way to analyze this phenomenon by means of ultrasonic methods is the same. The initial crack width in this study ranged between 100 and 200 microns. So in this picture you see the evolution in time that reveals that the healing effect progresses in time, allowing for a recovery that can be up to 100% depending on the exposure conditions. And in this study specifically, the exposure conditions were air exposure, water exposure, or thermal conditioning set to summer and winter cyclic days. The self-healing effect is also visible in the reference samples without crystalline admixture due to autogenous healing, but this is magnified in the samples with crystalline admixture when curing in air or in low humidity conditions are considered. And finally, a picture taken from a work by Agamri, Kanelopoulos, and Altaba, in which the variation of crack depth in time is estimated through ultrasonic pulse velocity, as I said before. The self-healing system here considered are concrete prisms made with lightweight aggregate impregnated with sodium silicate. So again, different self-healing approach, same analysis method or similar analysis method. These prisms were cracked in three-point bending with an average residual crack upon a loading of around 120–170 microns, and then cured in water after cracking. And they revealed a much higher crack sealing with respect to the control specimen, as confirmed also by visual inspection of the cracks. Ultrasonic methods based on the measurement of a pulse velocity are certainly the most used ones, but not the only ones. Our techniques address different wave propagation properties to investigate the transmission medium. For example, there are those based on attenuation of surface waves. Now, surface waves can generally carry a higher amount of energy than body waves, which allows them to propagate over longer distances and to detect the amplitude variation due to attenuation with a higher accuracy. Plus, they are constrained near to the surface of the material and are suitable to explore the behavior of surface breaking cracks. Since the transmission coefficient is affected by the presence of cracks as a function of the wave frequency, then monitoring the amplitude of the waveforms can provide information about crack evolution. And the typical setup for this type of test doesn't differ very much from the one used for the pulse velocity measurements, except that proper emitting transducers have to be used, and they can also be impact sources in the audible range. And at least 2 transducers are required simultaneously in such a way that the amplitude of the receiver far from the source can be related to the amplitude of the receiver close to the source. Indeed, the presence of crack in between the 2 receiving transducers contributes to absorption phenomena. So it causes a decrease of the transmission properties, and therefore the amplitude of the received signal is more attenuated than in sound materials. And obviously, if a healing phenomenon occurs, the situation is reversed, and therefore it's possible to define damage or healing indicators based on the amplitude ratio of the far receiver to close receiver, or simply the wave amplitude in controlled laboratory condition as a function of crack parameters. This is the approach that has been followed by Aldea and co-workers, who investigated the autogenous healing in this case, due to water in standard concrete samples cracked by controlled splitting tests. And in this case, different crack widths were examined. Also, Ellis and co-workers investigated the repair effectiveness of epoxy infiltration in concrete samples, the standardized cracks, using surface wave transmission. The cracks were artificially created by means of slots with 4 millimeters width and different depths, ranging from around 2 to 20 millimeters. And on the left, we see the effect of the damage. So the creation of crack on the transmission coefficient. The deeper the artificial crack, the lower the amplitude ratio between far and close transducer. While on the right, we see the effect of healing due to the partial epoxy infiltration, as recorded experimentally or simulated numerically. And here, the higher the percentage of healing, the higher the transmission. Another way to explore the wave-medium interaction is via nonlinear analysis. Nonlinear ultrasonic techniques have been demonstrated to be particularly sensitive to early-stage damage and microstructural evolution, and they can capture the nonlinear features induced by the presence of cracks through the observation of the system response as a function of the excitation amplitude. Specific nonlinear ultrasonic methods that have been developed at Politecnico di Torino is the scaling subtraction method. And the basic idea underlying this method is that damage and nonlinearity materials are strictly correlated. So damage in the form of microcracks or defects can induce a microscopic nonlinear elastic response characterized by wave distortion, generation of accompanying harmonics, multiplication of waves at different frequencies, resonance shift, changes in wave speed and attenuation as a function of the excitation amplitude. All this complex phenomenology causes a loss of proportionality between input excitation and corresponding elastic response. And the whole point is that all these nonlinear effects can be remarkably high in damaged material, while they are usually very weak in undamaged media or for low excitation. So imagine that you inject in the element under consideration a low amplitude ultrasonic excitation and record the corresponding output waveform. This doesn't contain any of the effect that I mentioned before because the excitation source that produced it had a very low energy content. So it can be considered as a linear reference independently of the damaged state. And if the system is really linear, then the superposition principle will stand true. And therefore, an excitation amplitude proportional to the first one would generate a perfectly proportional output response that can be constructed a priori based on the first output response apart from noise effects. But if the system is non-linear, for example, because it's damaged, then the actual output response will be different from the linear one. And all the nonlinear contribution at the higher energy is entirely contained in the difference between the actual output waveform signal and the linearly scaled one. This difference is referred to the scaled subtracted signal, and it's possible to define some quantitative indicator from these signals. For example, it's possible to define the theta and eta indicators as, for example, the root mean square over a given time interval, or simply the maximum. So we can plot an excitation protocol like this. For example, a series of successive pulses with increasing amplitude. This is the whole point. The first one is used to define the linear reference because it's a low amplitude excitation, and then the second and the following generate progressively higher nonlinear outputs. And they are used to calculate the scaled subtracted signals with the corresponding quantitative indicator. So eventually we can obtain a sequence of points in a theta versus eta plot for varying driving amplitudes. And these points follow a peculiar trend in which a faster increase corresponds to a stronger nonlinear elastic response. And this trend is found to be well interpolated via power law fitting curves. So an SSM indicator can be derived from the exponent of the power law fitting curve. And as I anticipated, the occurrence of nonlinear effects is expected to become more marked with increasing damage and therefore to decrease with progressive healing. Consequently, we can define damage or healing indicators based on the measurement of some nonlinear feature. And for example, we can use the SSM indicator that I mentioned before, or also other nonlinear parameters such as the ratio of higher order harmonic components to the first harmonic component, etc. And there's a picture taken from one of the works made by my research group where the effects of sodium silicate as a healing agent are explored as a function of healing time in air exposure using the scaling subtraction method. And the specimen here used were mortar prisms that were first split open in 3-point bending and then reassembled by applying a sodium silicate layer by brush on the fracture faces. The exponent of the power law fitting curves for varying driving amplitude was used as a nonlinear SSM indicator, and this one is shown to decrease in time with progressive manifestation of the healing. The chemical interaction between the cementitious matrix and the sodium silicate. And in fact, the indicator starts from values practically identical to the cracked samples, and you see them in the orange arrows on top. And then in the course of about 10 days, 2 weeks, this indicator tends to the value displayed by the intact samples, as indicated by the green arrow. Now, all the ultrasonic methods that I shortly described so far share some operational details for the practical implementation, and it's worth recalling them here. The first step to take before any practical implementation is actually making the initial technical choices In particular, selecting the frequency ranges and testing method as a function of the phenomenon to be investigated. In heterogeneous media like concrete, there are basically 4 different regimes that can be identified for 4 consecutive frequency ranges that identify fairly different behaviors in terms of wave attenuation and possibility to use the wave excitation to get information on the material. At frequencies lower than 20 kilohertz, so actually below the ultrasound threshold in the seismic and audible range, the wavelength of the elastic wave is greater than the macroscopic size of the structure, or of the same order of magnitude, and in this case, only stationary waves can be excited, corresponding to the vibrational eigenmodes of the structure. This is the frequency range of structure health monitoring and model analysis techniques, which are easy to implement but have limited sensitivity to local or microscopic features and poor resolution for locating defects. At the opposite end, for much higher frequencies in the megahertz range, intrinsic absorption is dominant, and this causes attenuation to increase to such an extent that the elastic waves can no more be detected on large length scales. So in this latter domain, ultrasonic techniques might be implemented only on very small size laboratory samples. In between, we find the simple scattering and multiple scattering regimes. In these frequency ranges, attenuation is mostly due to scattering, that is the complex set of reflections and interaction phenomena that occur at the interfaces with the heterogeneities. So when the wavelength is smaller than the actual structural size but larger than the average size of the heterogeneities, usually between 20 and 150 kilohertz, then the elastic wave interacts weakly with the heterogeneities. And conversely, when the wavelength is smaller than the average size of the heterogeneities or of the same order of magnitude, so beyond 150 kilohertz, then the wave can interact several times with the heterogeneities before reaching the detector. In this process, it is attenuated due to multiple scattering and transformed into a diffuse wave field. The ultrasonic techniques that I described in this lecture do not apply very well to this multiple scattering frequency range, in which other techniques such as coda wave interferometry or diffusion analysis methods have to be preferred. And remaining in the range 20 to 150 kilohertz, it has to be recalled that a better spatial resolution is obtained by increasing the frequency. But on the other hand, increasing the frequency brings about also an increase in attenuation and a reduction in the signal-to-noise ratio. So the optimization can really be obtained only considering the peculiarities of the problem to be investigated. And as for the detectors, they can be narrowband or broadband, depending on their output response and capability to detect vibrations with different frequency contents. Narrowband transducers are recommendable for simple wave velocity measurements because they normally have a higher sensitivity, while broadband transducers are required for more complex analysis, accounting for additional frequency components in the output waveform signals, but they are normally more expensive and less sensitive than their narrowband counterpart. Some operational notes about the application of ultrasonic methods regard the measurement setup and in particular the selection of the coupling agent. The whole goal of selecting the right ultrasonic couplant is to maximize the amount of energy transmitted from the emitter to the element tested over the air gap created by the transducer to element interface. But we also want to minimize the risks connected to the use of the couplant and the cost, time, and cleanup and stuff like this. So surface texture is a first factor to be considered because an element with a rough surface texture, like concrete, means that the couplant has to be thicker to fill the gaps and ridges and thus working more effectively than a thin, watery couplant like the ecographic gels that I mentioned at the beginning. Very thick and high viscosity couplant would be needed also in the case of vertical or hover-head inspection in order to cling to the test surface. And in addition, always a very thick and high viscosity couplant is required to couple shear waves, because gel and liquid couplants do not support shear stress. And in this latter case, it's recommendable to use a layer of couplant as thin as possible to reduce attenuation. Further factors to be considered are the environmental conditions. Just to make an example, for low temperature inspections, water-based couplants are not the best choice because they are more likely to freeze when temperature drops. But a better option would be to use a silicone or glycol-based couplant. Other factors to be taken into account for the selection of a couplant are its stability over time for long duration monitoring, its safety for both the operator and the material itself. In addition to the coupling, other factors related to the measurement setup may have an influence on the test results and should be carefully checked. For example, the analog-digital converter properties to avoid losing part of the information contained in the waveform signals. The gain settings to avoid signal saturation, the cable impedance adaptation to avoid interference, the signal synchronization when repeated excitations have to be applied, as in the case of the scaling subtraction methods, and so on. The testing condition and the specimen conditions also play a role, especially the moisture content of the element under investigation. This factor has to be controlled in case of multiple measurements on different specimens or on the same element over time in order to ensure an adequate reproducibility. In any case, always try to validate the setup under controlled conditions and share good practices with other researchers working in the same subject whenever possible. So now I completed a short overview on ultrasonic methods and related operational notes, so we can pass to the second part of this lecture regarding the durability test. Maybe a small break would be nice at this point, so if you agree, we can go grab a coffee and see you in 10 minutes, otherwise we can go on. You just tell me.
I think it's good if they have a short break, and then they can also ask questions if they have.
Yeah, maybe just 10 minutes.
Say we see at, yes, 10 minutes, that's fine. So, 5, okay?
Yeah.
Okay, grazie, thanks.
See you later. You're all there? Or you're still there?
Yes, yes.
And I see Tim too. Is that you?
Sorry, I did not hear you.
It seems to me I'm looking at Tim too. Is it you, Tim?
Yes, Tim is also here, yes.
Yes, hello, Paola.
How's it going with the management of this training network?
Well, I'm very lucky because the management of the training school is now entirely managed by the Delft team. So that takes a lot of work from my shoulders, but all of the other management is now quite hectic, yes.
Okay.
How are you?
I said to Eric, it shouldn't really be very easy to organize such an event completely online. I think Liberato too has to organize the self-healing conference in a remote mode, because I don't see any light from now up to May situation about the COVID infection is going worse in Italy these days.
Yeah, because right now you're in lockdown, correct?
Yes, we are. So teaching in the university, but also in schools, is completely in remote mode, except for the babies.
Oh, okay, yeah. But is
We are also
the International Self-Healing Conference is not
we are
in
not allowed.
2021?
Should it? Yes, it should be in 2021, but
yeah, right.
It's delayed. Well,
it's
this is
arriving.
Hello. I also
Hi,
joined
Nele.
for a moment, but I'm a bit surprised that I was thinking I would listen to your lecture, Paola, but you're just having a break or something, or
No, now it's 5 minutes.
Just 10 minutes.
sorry? You're just having a break.
Yeah, there is a 10-minute coffee break right now.
Ah, okay, I didn't realize. Okay, but I can tell you that I have been in contact with Liberato for the self-healing conference, you mean, ICSHM, because I'm a member of the steering committee and he proposed to postpone it by a year, so it will now be in 2022.
Okay, that's a good option because
yeah, the steering committee found the same, that it will be too hectic. Liberato is not able to make any reservations at the moment. And people just don't want to take the chance to make reservations for now in spring. So it's postponed.
The situation is not under control anymore. Things and rules are changing continuously.
Yeah, that's
we are. In summer, we were allowed to go anywhere. We were all happy. It seemed that this infection was disappearing, but
I thought, I had actually already foreseen that it would probably come back, but
yes, they were.
It doesn't just disappear, something like that.
No, yes, it's like.
But at least we had a break from it, and could have some holidays. So when is it supposed to start again? Because
I said five. So
5 minutes.
Less than
4:15.
Okay, so I will join then later to just follow a bit, but maybe not too long. I just wanted to. I was just interested in the explanation. Okay, see you soon then.
So Tim, we really need to find a way to make a test for the Teams connection for your PhD discussion.
Yeah, whenever works for you is fine for me.
I don't know, because maybe even tomorrow could be an option. The point is, I am now connected as Delft University, which is fairly strange.
Yeah.
What did you do, Paola?
No, it's because I think it's because I called her. She was not connecting, so I called her. So it might be.
Yeah, but Eric, I'm now also a member of Delft University according to my Teams.
That's good.
Yeah.
Did you also get a salary from Delft? So I don't know how you did the setup. For me, everything works. But it seemed to work, so that's good. So.
Anyway, if you agree, I can try and disconnect from Delft University and try to connect with the link that you will provide and make a test this way. And so for the rest of the training school, I will log again as Delft University. That could be an option. We just
but you're now logged in. Now stay in, because everything is working. So if you disconnect, maybe we have a problem. So it works like this.
But I think I can recover this connection information from my profile, because I see two of them now, Delft University and Politecnico.
Okay.
Yeah, that's what I have to do every morning. So when I log into my computer,
So
then
you
it
log in and
will
log
start
out.
Teams as UGent. That I can't change to Delft University. So what I then have to do is I have to log out of Teams, log back in with my UGent account, and at that moment I can change to the Delft University of Technology.
Okay.
So you can switch from one login to another.
Yeah, but if I don't log out first, then I can't do the switch.
Yes, that is expected.
So it's weird how it works, but it works very well. So congratulations, Eric.
Yes.
Okay. But everything you're saying now is also live streamed, so the whole world can look at it. Or
Yeah.
almost the whole world.
Yeah, you sent me the picture of your setup. It was quite impressive.
That's just at home, huh?
Yeah, well, I'm now wondering what your office will look like with
Yeah, it's
spaceships
empty
floating
because I
through
took
the
all the
air and
computers home. But what time are you continuing, Paola?
I think we should already start.
Okay.
You tell me, because I don't see the guys.
I think is it fine with everyone that we start again? I still do not see cameras on. Let's just wait for 1-2 minutes that they wake up. Now it's late.
Okay,
Last
then I
lecture.
can still get a coffee.
I just also see the question of Shan asking if we will upload all the presentations. So yes, all the presentations would be updated in our Teams. So myself also will upload my presentation as well.
So I can send my presentation to you, and can you upload it?
Yes.
I don't want to make any mistake.
No, just do so, and I
Thank
will upload both. No, it's good. Thank you. Okay, I think we can start. Now we are all here.
Good. So back again to continue with non-destructive testing methods for self-healing, and this time with reference to durability tests. So you all know, along with the intrinsic interconnected porosity of concrete, the presence of cracks, just maybe due to different physical, chemical, and mechanical causes, contributes to create pathways for the penetration of aggressive agents into the bulk material. And therefore, durability of concrete structures is strongly dependent on the ease with which fluids and fluid-borne aggressive substances can penetrate and diffuse through cracks. Water is one of the main vehicles, but liquids and gases can also be of interest for these substances to enter the matrix. So accordingly, different test methods have been developed to characterize the related material performances. But only tests using pure water without potentially harmful ions can be regarded as truly non-destructive, so they can be repeated over time to assess the self-healing effectiveness on the same specimens with no interfering actions. So when considering the water transport through porous media like concretes and mortars, two main mechanisms can be identified. Absorption, in which the fluid penetration is governed by the capillary suction created by surface adhesion forces, and permeation, in which the fluid penetration is governed by pressure gradient. In both, matrix microstructure plays an essential role, in particular, its pore size, distribution, and interconnectivity. And in both cases, damaged cementitious materials, also the presence of cracks, their size, density, geometry, and distribution are crucial factors. And therefore, capillary absorption tests and water permeability tests can be adopted as a way to characterize the effects of cracks, and conversely also to characterize the effects of crack closure in region self-healing. Let's start with a capillary absorption test. It's a very convenient test characterized by many advantages. Among them, we can list an easy implementation, a low-cost equipment, a direct measurement of the transport-related properties, and also the existence of reference standards for sound materials that can be adopted also for cracked specimens with few modifications. For example, the European countries can refer to the standard EN 13057 related to the determination of the resistance to capillary absorption of products in systems for the protection and repair of concrete structures. Such a standard describes setup for the absorption test as composed substantially of one rigid flat bottom basin with a lid and two simple supports on which the specimen can be placed in such a way that the water stays in contact with the specimen bottom face and covers it for a few millimeters during given time intervals. In the case of cracked specimens, the influence of the matrix on the absorption properties has to be minimized in order to emphasize the effects of crack instead of the porosity of the matrix. So the bottom needs to be completely waterproofed apart from a small area centered on the crack, which is called the exposure area. Consists in measuring the mass absorbed water at no less than 6 interval and calculating the sorptivity index. So the mass of absorbed water can be measured simply removing the specimen from the bath, removing the excess water and putting them on a scale, measuring the entire mass and continuing the process of absorption for as long as desired. And the sorptivity index can be expressed as the slope of the cumulative absorbed volume of water per unit of exposure area, plotted against square root of time. It is expected that the presence of cracks causes an increment of the capillary suction and hence an increment of the sorptivity index. And therefore, in self-healing system, a sealing efficiency indicator can be expressed as reported in this formula, where SU is the sorptivity index for unhealed specimens, and SH is the sorptivity index for healed specimens, and SI is the sorptivity index for intact specimens. Let's see a couple of examples of literature studies using this type of setup to characterize self-healing. The same work by Algamri, Kanellopoulos, and Altaba that I mentioned when speaking of the estimation of a crack depth by means of ultrasonic pulse velocity tests also included sorptivity tests to complement the analysis of the performance of self-healing concrete using encapsulated and lymphogenated lightweight aggregates. And here you can see that the trend of the cumulative absorbed water per unit area. The improvement with respect to the control material without lightweight aggregates can be clearly noticed, and by comparison with the sorptivity of impact materials, the sealing efficiency could be assessed as practically 100% on average. Things don't go always so smoothly when considering other types of self-healing mechanisms. For example, this recent study by Tim and co-workers used the sorptivity test to characterize the self-healing performance of concrete with encapsulated polyurethane in the frame of an inter-laboratory testing program involving 6 different laboratories from the construction circles. And here the observed sealing efficiency was limited to 14% for an average crack width of around 300 microns. So although quite disappointing from the point of view of the performance, this result is, however, very important because From negative results, one can learn possibly even more insight with respect to the positive results. And in this way, all the factors influencing the test outcome, apart from the execution of the test itself, can be highlighted and better controlled. So in this case, major influencing factors were ascribed to the capsule sealing with epoxy resin and to the capsule aspect ratio, which could have limited the polyurethane release upon cracking. Passing now to the water permeability tests, it can be highlighted that they offer similar practical advantages as the absorption test, and indeed also permeability tests are easy to implement, they require low-cost equipment and allow for direct measurement of transport-related properties. And also in this case there are some reference standards for sound materials that can be modified in order to study cracked and self-healed materials. In particular, European countries can refer to the standard EN 12390 Part 8, describing testing methods for the determination of the depth of penetration of water under pressure in hardened concrete. The experimental setup described in this standard for sound materials consists in a permeability cell by which the specimen can be connected to a pressurized water supply for a prescribed amount of time. And after that time, the specimen can be split open perpendicular to the face exposed to water, and the penetration depth can be measured directly by visual observation. Such a procedure is feasible for sound materials, but in pre-cracked specimens, the presence of cracks induces a measurable water flow rather than a penetration depth. So the setup must be changed, and different options are available to do so with constant head or variable head configurations, high pressure or low pressure settings. So in his PhD dissertation team, Van Molen summarizes the different configurations adopted in the literature according to this picture. There can be variable head setups with or without a lower reservoir. This configuration was studied, for example, by Nishiwaki and co-workers in 2014 and by Vartitavum and co-workers in 2016, respectively. In the first case, the focus was on the self-healing capabilities of high-performance, fiber-reinforced cementitious composites with different types of fibers, cracked by means of direct tensile tests in a range from less than 100 to about 800 microns and healed water. In the second case, the focus was on full-scale reinforced concrete beams added with superabsorbent polymers or with encapsulated polyurethane and cracked in focal-point bending. In both cases, water permeation caused a drop in the water height in the upper water reservoir, which was open towards the concrete, so that the water permeability coefficient for the given geometrical settings could be expressed as a function of the initial and final water head and of the time needed for the drop to occur. In this configuration, the water drop has to be measured at regular time intervals so that when the permeability coefficient becomes constant, it can be taken as the reference value for the material tested. Alternative configuration for the water permeability tests can be obtained with constant pressure setups, as achieved through constant head, with or without lower water reservoir in contact with the specimen, or through pressurized water supply. This is how other researchers conducted their experiments. For example, Shin and co-workers in 2017, Mechterling and Liebold in 2011, Palin, Jonkers and Victors in 2016. Their works regarded different objects in plain cement mortars with different types of cracks in water heads, textile reinforced concrete cracked under direct tensile tests, and blast furnace slag cement mortars cracked through splitting tests, respectively. Different objects, same or similar type of analysis, which which allowed to flow the different geometric configuration and hence the permeability coefficients as a function of the measured water flow. There's also another way to conduct water permeability tests through the evaluation of a water flow, as you can see in this last scheme. This is a constant head setup in which the water flow is obtained by means of a hole inserted in the specimen at the moment of casting, and then this hole is connected to a water reservoir for the permeability test. Such a test setup was first introduced in the framework of a European project, HILCON, and subsequently adopted in many other studies, such as in Gruyert and co-workers in 2016 for the evaluation of mortars with pH-sensitive superabsorbent polymers, and in Van Mullen and co-workers in 2020 for the assessment of cement mortars with encapsulated polyurethane. With respect to other water permeability test setups, it offers the advantages of a faster execution, easier detection of leakage by visual observation of the free lateral surfaces, and most of all the possibility to use specimens with realistic flexural cracks. So, in addition, such a water flow test setup has already been adopted in 2 interlaboratory testing programs, thus starting its validation process in view of possible standardization. The execution of such a test requires that the water container is connected to the casting hole through a plastic tube. Sealing layers are placed at the end of the hole and in correspondence of the lateral surfaces of the crack. And an automatic scale is used for the detection of the amount of water which is leaked through the bottom part of the crack in a steady state condition. And then the effectiveness of the self-healing in restoring water tightness can be evaluated as reported in this formula, where W0 and W can be either the water flows at given times in control, unhealed, and self-healing samples, or the water flows before and after healing. So in the first case, the use of a companion unhealed specimen allows to discern the differences produced by aging of concrete by comparing 2 specimens at the same age, while in the second option could be useful to reduce uncertainties due to the variability of the crack width. Recent application of this method is reported in the literature in the same study conducted by Van Mullen and co-workers that I already mentioned, and that investigated also the capillary absorption behavior in the presence of encapsulated polyurethane. So as you can see here, the permeability test returned better results with respect to sortility test, with a sealing efficiency exceeding 40% in most of the cases, up to 73%. Now, such a behavior compared to the one observed in the sortility test can provide an indication about the applicability of the self-healing mechanism based on the encapsulation of polyurethane itself. In fact, such a healing agent seems to be more fit for the purpose of enhancing the water tightness when water inflows are expected, as for example in tunnels, while other healing agents such as water repellents, for example, may be more helpful when damage due to infiltration of water by absorption is more likely to occur. Once again, both water absorption and permeability tests have in common some operational details that need to be checked. The first concerns the pre-cracking procedure, because the crack parameters such as width, tortuosity, and stability deeply affect the water transport properties, and therefore achieving a good control over these parameters is crucial for the purposes of measurement reproducibility. Also, the preconditioning procedure to control the moisture content of the specimen are extremely important, so they have to be implemented in opposite directions for absorption tests and water permeability tests. So a low temperature oven drying procedure is required for the samples to be subjected to absorption tests until mass stabilization to allow for the absorption phenomena to actually be manifested, while water saturation is required for the specimens to be subjected to permeability tests in order to avoid underestimation of the water flow due to partial absorption in the unsaturated porous matrix. Moreover, geometry-related factors may have an influence in terms of measurement reproducibility. For example, the exposed area in water absorption tests. The higher the exposed area around the crack, the higher the sorptivity due to matrix porosity, and the less distinguishable the effects related to the presence and healing degree of the crack. The position of the casting hole in water flow tests, because the higher the position, the more influent is the tortuosity of the crack, and then the variability in the data. Among the general settings, waterproofing is also a relevant factor to be checked because it has to be properly executed to protect the matrix from contact with water absorption tests and also to avoid undesired leakages at the connection locations in permeability tests. Adopting robust and efficient procedure to keep the control over the water levels is also very important for both absorption tests, in which the level of the water in contact with the specimen has to be controlled, but also in constant head water flow tests. Whenever possible, try to make durability test setups under controlled conditions and share good practices with the expert in the field. In conclusion, we have seen that many implementations of ultrasonic methods and durability tests can be successfully set up to assess the self-healing efficiency and the self-healing performance in a non-destructive way with different self-healing approaches, either in the lab for the purpose of self-healing mechanism validation and optimization, or on site for the purpose of monitoring the self-healing performance in time in real operating conditions. Now it's just time to decide which one is most suited for your applications or which one can be further improved to provide more reliable information. And you have already been assigned your project in which you have to work during this training school. The Lessa with swimming pools in Porto. You have been asked, how are you going to investigate, inspect the problem areas in this structure? So of course now I can add, are you planning some non-destructive testing? What are the possible problems that you're going to look for? And in this case, which non-destructive testing techniques are most suited to the purpose? Are maybe some of the ones that we have already seen today convenient? Or can you detail how to implement them? And how are you going to solve these problems by making use of self-healing materials? This is up to you to decide. But once you have decided what kind of lab research do you need to optimize your product and solution, can you maybe set up a laboratory pre-qualification plan using non-destructive testing and water absorption or water permeability tests in particular? How can you integrate your test results and obtain more reliable information by performing complementary tests? How are you going to monitor if your product will work? Can you compare the performance before and after healing directly on site? And what do you need to do so? So all these issues, I let them to you to think about and discuss with your team, also with me, if I can be of any help. And I will say thank you for your attention. If you have questions, maybe someone can help me find the chat.
Yes, maybe we can first start here with questions. I do not see any. Let me see the new questions. No new questions in the chat. So let's see if there are questions here in the group.
Hello, I want to ask a questions that, for example, when we do the non-destructive testing, for example, using the ultrasonic waves, sometimes if we check on the concrete, which is like maybe already pre-cracked, how we can mitigate to optimize the waves, because sometimes we can get like a high attenuation or we can have the high noise. So how to reduce it so we can have like the clear peaks on the signal? Thank you.
That's the crux. If you start by analyzing a cracked element, it's hard to find the right setting that can be maintained for all the testing. If you're also observing some healing, because meanwhile the attenuation decreases and you risk saturating your signals. One possibility could be to use nonlinear techniques, I think. They are more sensitive to damage, and if the damage is not so high, you can possibly use the same settings all along your testing campaign. You also have to be very careful about coupling, because you can miss a lot of the energy, you can lose a lot of the energy at the interface between the ultrasonic sensors and the surface of the element you're testing. In the end, if you don't see much at the beginning, you can see better signals after, as soon as healing is starting to take place. What kind of examples do you aware of? Do you already have experience with some practical case?
No, at the moment I don't have any experience like doing the ultrasonic measurement using the concrete. However, like my previous project, I used the NDT technique to do the setting time of the cement paste.
Okay. I guess selecting the sensors and the frequency range of the sensors as a function of the size of the specimen you're analyzing is the first thing to do. I would suggest to do it first on sound elements, because in this case you're absolutely certain you don't saturate your signals. You can adjust the gain at the minimum possible, so you have the maximum range to set up your measurement systems later as soon as the cracks appear.
Paola, I would like to ask a question, if I can.
Sure.
I think that the great thing about non-destructive testing is that you can combine it with other analysis methods, because in essence you do not disturb your specimen. But for example, if you are looking to liquid tightness, are there special boundary conditions we should take into account with respect to, for example, the sample size? If we look at certain of the permeability methods, they might have, for example, the cast in hole. I assume that this will greatly influence the results that you could get from studying, for example, the waves that you send and receive.
That's the reason why it is important to agree on some testing methodologies. And your work in this sense is extraordinary. You're already paving the way for standardization, as you said in your paper. Yes, it's important to fix some points, for example, the scale of the element to be tested. In this way, the results can be more comparable. It's just a matter of agreeing, I think, because if you're using non-destructive testing for the laboratory development phase, you just have to you're free to ignore aspects like the real structural size. You can focus your attention on the healing, on the local phenomenon due to self-healing or due to damage. And in this case, you can use a size which is representative of concrete element, but you don't really have to test full-scale elements in the lab. But if you want to make your results comparable, you have to agree on a size which is representative enough and can be reproduced in all these sort of tests, if this is what you meant.
Yeah, okay, yeah, no, I understand you completely. Thank you.
So how are you going to work on your projects? Do you have a strategy in mind? Do you have some starting point?
Yeah, we already start some experiments in my case, and I inspired for the work of Tim with water permeability tests that he already applying his work as well.
And what kind of self-healing? Are you working on self-healing, right?
Yeah,
Not
with self-healing.
What kind of self-healing strategy are you planning to explore? And
for now, I try to use it to different types of healing agents available in the market. It's two commercial products, a crystalline mixture and a bacteria in a power way. And yeah, applying one of extreme conditions inserting into my project. I have one question regarding to the water permeability test, more related to real scale, because now we have a project to work in this, and when we work in the lab, it's easier to work with a specimen, but in what you suggest something to apply for measure permeability in situ, or yeah, it's more complicated to do this in situ.
Yes, it is. The obvious first thing one you can think of is to pour some samples from the structure you're analyzing. So in this case, you can select first the locations that need to be explored, because they can be problematic, and you can select them by using truly non-destructive methods. For example, you can use ultrasounds or other techniques to select the portion of the structure that you believe that can be problematic, and possibly you can also identify the other areas of the structure that, on the contrary, are in good health. So you have two types of areas representing different states of damage, if you're looking at the damage. After that, after you have been using this type of techniques to select the areas, then you can try and core some samples that you can test in the lab. And while coring and extracting samples from the structure, you have to be very careful not to add some additional form of damage. So you have to be very careful in handling the material that you extract from the structure, and to keep in proper conditions when you test them, always in a very comparable way. So you don't have to induce any other further elements of disturbance. Either when you take the material out of the structure or when you test them in the lab. So once you have a core sample, you can probably test it in the same way as we've done for ad hoc specimens.
Yeah,
That's a possibility. Otherwise, you have to think of something different. But it's hard to quantify in this case.
yeah. Thank you.
Hello, Paula. Thank you for your presentation. It was very informative and useful. I just have a very practical question. Very often the question of representativeness comes in when we do the non-destructive testing for one particular region. So if it's like a very large beam, we are testing for its soundness, say even the compressive strength. Sometimes we can have patches of loss in strength when we are taking the measurements, but very often we focus on only one small region because we cannot measure for the entire beam. So how do we normally tackle the issue of representativeness? Because when we take the values, it need not necessarily be the same in another position of the beam, which we could not measure.
Well, indeed, this is a challenge. If you try and collect as much as you can know about the construction, the way the structure was constructed, you can envisage some problems that may have been generated during construction because of the geometry and because of the way beams are constructed. So if it contains a very dense rebar structure inside, it can be that the casting itself could have had problems, and so if you want to select an area representative of defects in the matrix, you can probably look around the rebars, because in that region maybe the flow of the fresh concrete could have been hampered by the rebars. If you know that some defects can have been introduced because of the aggregates, because they were not adequate, you can probably select any region. And if you are expecting that some carbonation effects are present, of course you have to select the external part as representative of the problem. I think the best would be to deepen the knowledge about the construction, about the history of the element that you're testing, so as you can in some way imagine what kind of problem and how they can have affected the structure as you see it at the present moment. And so you can extract some material from that specific region.
Thank you so much.
No problem.
Okay, are there any more questions or points to discuss? Or are you all ready for today? You say, we are done, we need a rest, or you have to work on the project, that's also important.
Okay.
I see no more questions, Paola. Then thank you very much for joining us today and giving a
Thank you for
wonderful
inviting
lecture
me.
and having a good discussion with all the students. That's appreciated. And probably see you back on Friday.
Yes, I hope
Okay.
so, and the next days too.
Okay,
So,
good. Okay, thank you, Paola.
thank you.
And
Bye.
Thank you.
you guys see you all tomorrow morning at 9. Then we start again. So have a good rest and wake up fresh tomorrow and then ready for another full day of lectures. Okay, see you tomorrow.
Okay. See you. Bye
See ya.
bye.
Bye
Thank
bye.
you.
you.
Bye.